Right, so we get to list coloring now. List coloring is a generalization of coloring where the vertices or the edges of a given graph have lists of admissible colors associated with them. So, for example, we have permissible colors 1 and 2 at this vertex, 1 and 3 and 0 at this vertex, and only 2 at this vertex, or something like that. And then the task is to find the coloring that picks the colors for the vertices that have these lists associated with them from their list. So here, for example, we could choose 1. Then here we're not allowed to choose 1, but we could use 3. And then here, luckily, this is a 2 and not a 3, so we can use that. Right, so that's the idea of list coloring, and it exists for edges as well as for vertices. So the list-chromatic number is abbreviated as CH, obviously. So that's the smallest k, such that for all lists, for all k lists, G has a vertex coloring from those lists. Right? For every choice of a list of k admitted colors for every vertex. Now, why is the list chromatic number called CH of G? Because it stands for choice. Right? It's the choice number. You choose from the lists. And this is the same for edges. And it's called the list chromatic index. Right? Remember, the edge chromatic number was also called the chromatic index, denoted by chi prime. So this is choice prime for the list chromatic index. Right, so is that bigger or smaller than the associated chi or chi prime? Well, coloring, ordinary coloring, K coloring, requires us to color from fixed lists, those with colors 1 to K. And asking that we can color from any lists of size K is a harder problem, because our adversary can choose those lists. Right, so it's a harder problem than coloring. So clearly, the choice number is at least the chromatic number. Well, let me just write that without the G's. And the same for edges. Simply because it's a more general, a harder problem in general to list color than to just color. At the same time, it seems that the difference between arbitrary lists and fixed lists of colors 1 to K is not something that really ought to get in the way, right? It's good for us if the lists for different vertices, say, are very different, because then we can sort of, we want colors to be different. So how can it possibly do any harm to have lists other than 1 to k? It might seem that the chromatic number, or the chi lists, of fixed lists of colors 1 to k, are something like the worst case. Therefore, maybe there's in fact equality here. And that is not the case. And I think I want to give you an example. No, not just yet. I'll give you an example in a moment. I'll tell you what is the case, and that is something quite extraordinary. So that's theorem 541. That's due to Noga Alon, 1993. And that says that the list-chromatic number, the choice number, can be pushed up by making the average degree large. Right, so formal statement, for every, there exists a function from the positive integers to the positive integers such that for all graphs G and for all K, if the average degree of G is at least f of K, then the choice number of G is at least K. So you can wish for any K that you like. You wish for a high choice number, and you can enforce that by choosing the average degree big enough, where big enough depends only on that K, not on the graph. Right? So that's quite something. So example, K and N. Now, K and N has large average degree, and so when N grows, this will exceed any function, in particular this function of 2, and therefore, or of 3, and therefore the choice number of K and N will be bigger than 3 when N gets large enough. Indeed, it will be bigger than any K when N gets large enough. Right, and so that's, that makes the list-chromatic number, the choice number, somehow very different from the chromatic number. The chromatic number is totally mysterious, as I hope I've sort of got across to you. It's a very strong assumption to say that a graph needs K colors. It has lots of consequences. It has large max degree, it has subgraphs of large min degree, and therefore subgraphs that are highly connected. Everything, all these things follow from the assumption that a graph needs many colors, ordinary coloring, right? But conversely, it's very difficult, as we saw last time, to find conditions that imply that the chromatic number is large. Okay, and for the choice number, this is different. This goes both ways, right? So it's more amenable to this interaction between invariants that we want to study in graph theory. And you might argue that the choice number is the more natural invariant. You might also argue that the chromatic number is particularly fascinating because it just cuts across all these things that we'd like to be true. It remains mysterious, whereas the choice number is a little less mysterious, even though it's so complicated by definition. So let me give you an example for K33. So that's K, 3, 3. And the example is we have lists 1, 2, 2, 3, and 1, 3. And the same on the other side, 1, 2, 2, 3, and 1, 3. Now, yeah, let's try and color this. Right, so by symmetry, we may as well assume that this gets colored 1. Right, then we're not allowed to use 1 here, and we're not allowed to use 1 there. Then next, we have to use 2 here. So let me make this a 2. That means we're not allowed to use the 2 here, but we don't want to anyway, because we've colored it 1. We're not allowed to use 2 here either. That, of course, means that we need to use color 3 here. Right. This. Which rules out color 3 here. And it also rules out color 3 here, but then we haven't got a color left here. So I didn't make any particular choices that were bad for us. I just made one initial choice, which by symmetry is not a restriction. And then everything else followed. Right, so K33 cannot be list colored from arbitrary lists of length 2, but of course it can be 2 colored. Yeah, I think that's all I want to say at this level. Any questions? No. Then let me give you the first theorem. Well, one more general remark. I said that maybe the choice number is the more natural invariant. It is quite remarkable that all these theorems that we've proved, like Brooks's theorem and greedy algorithm and so on, all these proofs still work for the choice number. We bounded the chromatic number from above, so bounding the choice number from above is harder because it can be bigger. But all these proofs do that. So, yeah. If you just look at those proofs again and rerun the proofs with lists, everything works. And the same is true for the 5-color theorem. So let me prove that in the list version. 5 of 2, every plane graph is 5 list colorable. And it has a very nice, very short proof. In a sense, it's shorter than the standard 5-color theorem proof. Well, not shorter than the fantastic little contraction one that I gave you as the second proof. That is really brilliant. But it is shorter if you take into account that for the standard 5-color theorem, we needed Euler's formula. Right? We needed to find a vertex of degree 5. And the reason that existed was that we can't have all vertices have a large degree, and that followed from Euler's formula. So Euler's formula, in turn, needed sort of half of the planarity chapter or more. So there was quite a bit of machinery, if you do it properly, that went into that. And there's no machinery going into this. And it's a stronger theorem. So this was proved by Carsten Thomason when 1994. Okay, so let me give you the proof. Thomason is a master of induction. He has all sorts of very, very clever induction proofs where the art lies in fine-tuning the condition, the induction statement, exactly right. Make it a little stronger, and you have more to use in the induction step, but you also need to prove more. Make it a little weaker, you have the opposite. So getting that right is an art in itself. It's not an art that I'm at all good at, because I mean, it's just, you have to be, I don't know, you have to either play around or you have to be brilliant in some way that eludes me, but he can do it. So here's the proof. And the proof is one for the following statement. I'm not going to write it out, but I'm going to tell you the statement. We prove something for graphs that are nearly plane triangulations. Right, it's enough to prove this for maximally plane graphs. We know that maximally plane graphs are plane triangulations. So we'll prove it for something slightly more general than plane triangulations, namely graphs, plane graphs, where only the outer face is bounded by some cycle that may be longer than 3. All the inner faces are bounded by triangles. We have lists of lengths three. No. For all except 2 of the vertices on this outer face boundary, we have a list of color of length 1 for one particular vertex and a list of length 1 for its neighbor. And these colors, I call them 1 and 2. And we'll have any lists of length 3 on the other vertices here. And inside, we have lists of length 5. Okay, and the statement is that any coloring from the statement is that whenever you have such lists in such a graph, this coloring here can be extended to a proper list coloring of the entire graph, or equivalently, there exists a list coloring from these lists here, if we think of those as lists of length 1. Okay, so is the statement clear? Right, for every graph, a plane graph, whose faces are all bounded by a triangle except the outer face, which is bounded by some cycle, possibly a triangle, maybe longer. 2 adjacent vertices on that boundary of the outer face have lists of length 1, and their colors are 1 and 2 respectively. And the other lists on the outer face boundary have length 3, and any other vertices have lists of length 5. Weird statement. And then we can list color. So that clearly implies that every plane triangulation is 5 colorable, 5 list colorable, right? Because if we have a plane triangulation, it's an instance of such a graph where the outer cycle happens to have length 3. And on the face that, on the outer face boundary, which is now a triangle in the application, we have lists of length 5, and for these two vertices here, we delete all but one of these colors from those lists, and for the remaining vertex, we delete 2 of those 5, up to 5 colors, to retain 3 colors, and then we are in this scenario here. So it clearly implies what we want. And the proof has 2 cases. Case 1, let me call this C, this cycle here. Case 1, C has a chord. A chord of a cycle is an edge that is not an edge of that cycle, but joins 2 of its vertices. So something like this. This happens to be one of the special vertices here. It doesn't, that's not by intention. I mean, it's allowed, but I don't want to just consider that case. I'm considering the case where we have any chord on C. Can you see the induction step? Yeah? Yeah, well, we'll do the upper half first, right? So we'll have 2 special vertices here. We'll just cut this short. This is a smaller graph. 2 special vertices. All the other vertices have lists of length 3. Inner vertices have lists of length 5. All the same as before. So we can color that from the lists. When we're done, these 2 yellow vertices have colors. Even if this is not one of the special ones, right? They have colors. And then for these prescribed colors, we can color the rest. Done. So that's the first case. Case 2, we don't have a chord. So in that case, we look at the last vertex here, call it vk. So if this is v1, this is v2 perhaps. So the last vertex vk, and consider all its neighbors. There's a path from vk minus 1 amongst its neighbors here. Warning flag. This requires, to get this formally precise, requires the sort of horrible pedestrian topology that we're used to do. Right? So you can look at a small neighborhood around vk, and then you have all these straight line segments getting out of there, and they're ordered cyclically. Right, remember e to the I theta or whatever. And we can find the cyclic ordering, and then these do indeed form a path. So I don't want to do that now. We got over that chapter intact, so I don't want to get back in there. Just a warning that if you do want to be able to do it properly, that ought to be part of that. Okay, so let's consider this path and apply induction to everything in here. So the graph minus vk. With the following lists. Vk minus 1, or let me start with Vk. Vk had a list of 3 colors. Let's call them J and L. if 1 is one of these colors, I don't want to call it J and L. I want to use the question mark to designate there's 1. Maybe 1 isn't among them, then it's some other color. It has a 3 list, right? Possibly including 1, possibly not. Okay, now delete J and L from these lists here. So this has a list here where maybe J and L are among the 5 colors allowed. If so, delete them. Okay, then we have lists of at most 3 colors left in here. And, sorry, of at least 3 colors left in here. We had a 5 list first, and then we deleted J and L. And then we'll have a list of at least 3 colors left, and the same for here and here. And now we use induction to color this thing here from the list with these 2 special vertices as before. Okay, and then we want to extend that to a coloring of the entire graph by coloring VK as well. So how can we color VK? Well, we want to use either J or L. We know that J or L are not 1, so that's fine. And J and L are not going to be used on these neighbors of VK, not on that neighbor, and not on these inner neighbors either, because we deleted J and L from those lists. They might be used on VK minus 1, but not both of them, only one of them at most. And we color this with the other. Yeah. So that was easy. Questions? No. Okay. Then let's look at the greedy algorithm. So if we have a graph, and every vertex sends fewer than k edges back in some enumeration of all the vertices, then there's a coloring from any k lists. Right? If we have lists of length k associated with these vertices, we just greedily color as we used to. We are sending fewer than k edges back, and we can always find one more in the current list. And it doesn't matter whether these lists use the same colors or not. Okay, so that was easy. Let me make it complicated. I'm not going to prove more now. I'm going to prove the same thing by induction. Okay, here we go. Run the greedy algorithm, and notice and note down the set of those vertices, call a U, that got color 1 from the greedy algorithm. Just give it a name. Orient all the edges backwards. All the edges. Orient them all backwards. Then the following is true. Every vertex that is not in U sends an arrow, an oriented edge to U. Otherwise, we would have put it in U, right? Greedy would have made it green if it didn't have a neighbor in a back neighbor in green. And this is an independent set. All right, so U is independent, and every V not in U sends an oriented edge to U, oriented in this orientation. That's just this observation here. Right, so where's the unnecessarily complicated proof of this trivial fact that a list of length k suffice to enable the greedy algorithm to always color from those lists? If we have this statement here, well, the proof is that we run greedy, we don't look what it does with all these vertices except U. And then we delete U. We color U with color 1, and then delete it from the graph. And then we notice that the lists of these vertices here, we can delete 1 from those lists without violating the assertion that for all V, the length of the list is at least k. Right, that was our initial assumption. Now k is dropping by 1 because we've already colored U, we're deleting U. Now we need to color the rest with k minus 1 colors from their lists. And we're making the lists a little shorter by deleting, whenever color 1 occurs in one of those lists, deleting that color from that list. So why does that maintain this for k equals 1? Well, because either we didn't delete anything from a list, for this vertex here, or if we did delete color 1 from that list, then this is because it sent an edge to U. Sorry, I want a slightly different statement here. This, that the lists are always longer than the out degree. Right, so that's true to start with. The lists have length k, and then when we delete this U, some lists stay the same, but then the out degree also stays the same. And some lists got shorter by 1, but then the out degree also dropped by 1. So we can just apply induction to the rest. Okay, so that's greedy made complicated. And the reason I made it complicated is that I want to use it. And here's a lemma which I want to use later. It's 5, 4, 3. Before that, let's give this a name. Such sets U are called kernels. So what's a kernel? A kernel in an oriented graph or in a directed graph is a set of independent edges such that every other vertex sends an arrow, an oriented edge to that set. Okay, so a set of independent edges so that every other vertex sends at least one oriented edge or directed edge to that set. Such a set in a digraph is called a kernel.
A set of independent edges?
Independent vertices. A kernel is a set of vertices. Okay? Right. So here's lemma 5, 4, 3. Let H be a graph with lists at the vertices SV do I want to give them? No. Right? A graph with lists at the vertices. If H has an orientation D such that for every induced such that, well, two things. So let me give the degree condition first, such that for every V, the out degree of V in this orientation, oh no, I want that for, no, that's fine. The out degree is smaller than the list length. And second, every induced subdigraph of this oriented graph has a kernel then there's a coloring of H from its lists. Okay? That's the statement. Given any graph, the only reason I'm calling it H is that this will later be used as a lemma when the real graph is called G. So H is any graph, and it has lists of the vertices, and we're requiring two things. One is that, well, we're requiring that it has an orientation. So we choose an orientation of the edges of H once, but we're allowed to choose one such that two things happen. One is this orientation has to give every vertex a small outer degree, smaller than its list length, as we did in greedy. Right? And the second is that not only D itself, but every induced subgraph of D has a kernel, as here. Right? So here, greedy found a kernel. And the induction worked by deleting that kernel. And we're going to do the same here now in the proof. So let me prove that. So we're doing induction on the order of H. Let alpha be any color from the lists. Then we have any color that occurs. Then look at those vertices where alpha does occur in the list. There's at least one vertex. So we're assuming this orientation, D. And now we also know that every induced subgraph and here we take the subgraph induced by those vertices where alpha does occur, has a kernel. So here's the kernel. All the other vertices here, where alpha also occurs, they all send an edge to that kernel, because it is a kernel, to that independent set of vertices, sorry. Yeah. Right, so here's an independent set of vertices. Now, D has a kernel, D prime has a kernel U, color U with alpha. Right, U is independent. We can happily use the same color, and alpha is a color that is available at every vertex of U, so let's use that. and color U with alpha. And then delete alpha from other lists. Apply induction. To H minus U. And that's it. So we delete U. U got colored 1. Got colored alpha. These lists here get shorter, but their out degrees also get shorter. So for the induction hypothesis, we can use the same orientation D. And with respect to that orientation, the out degrees either didn't change, so for vertices here the lists remained the same, or they did change, they got shorter. That's dangerous if the list got shorter, but then the out degree also got shorter, got less. Okay, that's it. Questions? It's sort of just a glorified version of this greedy triviality made complicated. Okay, then I have a question. Where did we use the assumption, this assumption? There's an easy answer and a nearly easy answer. What's the really easy? What's the really easy answer? Simple answer. Well, I did mention it, right? In the induction step, I used this and I said, oh, well, but it's maintained in the induction step. But then that's sort of a circular argument. What if I weaken this condition and just ask that the out degrees are less than the list lengths plus 100? Then everything still works. Ah. What's wrong? Yes, everything I told you still works. One thing I didn't tell you doesn't work. That's the induction start. Right, so at the induction start, we have, say, a K1, we have one vertex, and we want to color that. So we can color it because we're assuming it has at least one color in its list, namely more than its degree. Okay. Right. Another remark, crucially, for this proof, the list lengths are variable. We can't do the proof when all these lists are always required to have length k. And that's one of these things that make the proof pretty. It's something, this flexibility magically features in the proof, and then at the end of the day, and when we apply that lemma, it won't be there anymore. We won't need variable list lengths in the statement for whose proof we are going to use the lemma. But the lemma wouldn't be true if it wasn't stated in this greater generality for variable list lengths. Questions? Yeah? No question? Questions? Okay. Then let me tell you the list coloring conjecture. And that is that when we edge color, the list chromatic index is in fact no bigger than the edge chromatic index, than the chromatic index, than the edge chromatic number. Okay, so we know that this is at least as big as this. Same trivial argument as earlier, because the problem is harder. We have to, this problem to k-color the edges in something is a special case of that problem where we have arbitrary lists on the edges of length k. So the assertion is that this is in fact no bigger than that. So for vertex coloring, this is false, right? As I showed you earlier, the choice number can be bigger, in fact a lot bigger than the chromatic number. K and N was that example. And even other graphs whose average degree is large enough will have choice number as large as you like. And the conjecture is not so for edge coloring. Now, as you remember from Menger's proof, edge Menger, edge coloring is the same as ordinary coloring for very special graphs, namely for the line graphs. Right? Remember the definition of a line graph, if not, look it up. You have any graph, the edges of that graph become the vertices of the line graph, and adjacency remains what it is. Coloring the edges is the same as vertex coloring the line graph. So there's some hope for this to be true only because line graphs are such a very special class of graphs. In particular, K and N's can't be line graphs. So, yeah, that's why there's hope, or it's not completely out of the question, and we're going to prove the theorem for bipartite graphs. That's yet another restriction, and that is due to Galvin, 1995. So that's theorem 544. Fred Galvin. Was it 95 or 94? 95. Okay. True for bipartite graphs. Okay, and now comes a totally magical proof. The magic appears only in the last line, but it's really, really, really nice. So let's start on autopilot. Yeah, we need to show so proof to show this inequality that we need to show, that the choice number is no bigger than the chromatic number for the line graphs, for the line graph of G. Let's give it a name. let's call the chromatic index of G K. Let any coloring be given, so let C be any K edge coloring of G, right? We'll show that the choice number of G the choice chromatic index of G is at most K by showing that for all lists on the edges of length K, we can color the edges from those lists, and in doing so, we may use this coloring C that we know exists. Right? So we use the information that we have that the choice number of the line graph is smaller than the chromatic number of the line graph by picking a particular coloring of the vertices of the line graph and calling that coloring C, and then we're going to use those colors in the proof. So we'll show that the line graph H of G has choice number at most K, but I think I want to say something more special. No, let's just phrase it like that. Satisfies choice number of H is at most K. Right, so that's what we're going to do. Questions so far? No? Okay. We're going to use lemma 543 to do that. All right, so 543 says that a graph can be colored from lists on its vertices if something happens. And we're going to apply that with fixed lists containing colors 1 to K. Right? So we'll show that the line graph has the choice number at most K. No. Right. We want to apply that, and in order to get a coloring from the list, from the given list, we need an orientation. So to apply this, define an orientation on H as follows. Now the edges of G are the vertices, the the edges of H, which we need to orient. Right? Got that? So H has an orientation. H has edges. The vertices of H are the edges of G. So we need to orient the edges of H. Let me draw G. So this is G. And G has an edge coloring. So we use that edge coloring now with at most k colors. Let me draw some colors here. This edge has color 3, this edge has color 2, this edge has color 1. Maybe I want color 1 here and color 2 there. Right? So the edges of G are colored with k colors. Now I want to orient the edges of H. If this is E, let me write provocatively, that's a vertex of H. And another vertex of H, this edge here, and maybe here there's another vertex of H, another edge of G. So we have this E is adjacent to F. They're adjacent here as edges of G, therefore they're adjacent in the line graph. They're adjacent, E is also adjacent to G in the line graph because they're adjacent as edges of G. Now I orient an edge of H whose vertices as edges of G meet on the left from the edge color, carrying the bigger color to the edge coloring the smaller color. So this E here has a bigger color than this F. So the edge EF, no. The edge EF is oriented from E to F because they're meeting here, right? And F is adjacent to this vertex of H, and the edge of H between F and this edge of G is oriented from F to that edge of G because in the coloring, in the edge coloring of G, that other edge has a smaller color. So if we're orienting from bigger to smaller, when two edges of G, vertices of H, meet on the left in G. When they meet on the right, we do it the other way around, smaller towards bigger. Okay, so this edge E has a color that's bigger than this edge, this white edge here, whose color is 1. So we orient small to big because they meet on the right. And here, these two get an arrow like this. Okay. Okay, so what I have done now is define an orientation of the edges of H, using that the vertices of H, being edges of G, have colors, and that these vertices of H as edges of G meet either on the left in G or they meet on the right in G. Okay. Now, we're trying to apply that lemma. I've given you an orientation, that's D, and now we have to show the two bullets. First bullet first. For every vertex, the out degree is smaller than its list length. Now, the lists all have length k by assumption. Right? This is what we're showing. The lists have length k, so let's look at the out degrees. Pick any vertex, like E, vertex of H. What's its out degree? Well, it's adjacent to some other vertices of H, other edges of G. Or either they meet on the left or they meet on the right. If they meet on the left, the out degree, or the out edges from H, always go to edges of G that have a smaller color. If they meet on the right, and E meets some edges on the left and meets some other edges on the right, they go to other edges of G that have a bigger color. These are two disjoint sets of colors from a set of k colors. And these colors are all distinct here. The bigger ones are all distinct because they're all adjacent. The smaller ones are all distinct because they're all adjacent. So we have an out degree. This E can send orange edges only to fewer than k other edges because they're all colored distinctly in the edge coloring of G. And E itself also has a color, so that color isn't available. Okay, so clearly, for every vertex of H, let me write E of V of H the out degree is less than k. Now we have to check the other condition, the other blue bullet. So let G be any induced subdigraph of D. We have to show that it has a kernel. Okay. need to find a kernel. Kernels are green, so to find a kernel U in D prime. The kernel has to satisfy two things. The kernel has to be a set of independent vertices in this oriented graph. So it has to be a set of independent edges of G. Pairwise non-adjacent vertices of H, well, pairwise non-adjacent vertices of D prime. Therefore, pairwise non-adjacent vertices of D. Therefore, pairwise non-adjacent vertices of H. Therefore, pairwise non-adjacent vertices, edges of G. What's a set of pairwise non-adjacent edges? Yeah, it's a matching. So we need some matching, some set of independent edges of G. And now, with 15 minutes to go, I've arrived at the last line. This last line is a little longer, but still. So, when shall I let this cat out of the bag? Okay, I'll do it now. This is going to be a matching from the stable marriage theorem. Right? Stable marriage theorem that we have for every set of preferences at the vertices of a bipartite graph, there exists a stable matching. Okay, we want a matching, and my claim is that this will be the stable matching that the stable marriage theorem gives us for one particular kind of preference list. Okay, what are the preference lists? For every vertex V, no, left or right, doesn't matter. Edges G and G prime at V in G. I have to tell you which is bigger. Right, so a preference list is just a linear ordering of all the edges. So we are ordering the edges at any given vertex. So let E be less than E prime in the list associated with the list of preferences at V if the edge from E to E prime between E and E prime is oriented from E to E prime and D. And it doesn't matter whether V is on the left or on the right. Right? For vertices on the left, any two edges, both at that vertex, are linearly ordered by those colors, but it doesn't matter. What we remembered was that we have an orientation, an orientation from here, the bigger to the smaller vertices, here from the smaller to the bigger vertices, but whichever way they are, it doesn't matter. For every vertex V, there's a linear ordering on the incident edges. And we're using that linear ordering now to make our preference lists. Right? So we're defining E to be less than E prime if the edge between E and E prime is oriented in D from E towards E prime. Okay. And now we have all the ingredients for the stable marriage theorem. Stable marriage theorem says, well, when we have preference lists, so now we do, there's a stable matching. There it is. Now we want this matching to do something. We want it to be a kernel. So we want every other edge to send an oriented edge of D to some matching edge. In order to check that the matching is indeed a kernel. So for every other vertex of H, for every other edge of G, we need to show that in D there's an arrow from this edge to a matching edge. Now, what does the marriage theorem tell us, the stable marriage theorem tell us? It tells us that there are no subversive edges. When is an edge not subversive? If at least one of its ends is happier with its partner than with it. Right, subversive meant that both ends of that edge prefer it over their current partner. And that isn't the case because it's a stable marriage. Right, so this U is stable, and therefore for every other edge, at least one of the two end vertices of that other edge prefer their U edge over this. But what does it mean that they prefer their U edge over this? So when this is E, being preferred means that D orients the edge from E to E prime, just as we need it. Isn't that nice? Static.